No.
Can you hear me now? Okay, good. Hello, welcome to Aspen Center for Physics. My name is Marisa Walbert. I'm the Office and Communications Manager here. I do expect some folks to be kind of straggling in with the weather, so if you would just be mindful as they kind of filter through and make some space for them. Please make sure you turn your phones to silent, please and thank you. Next week's lecture, The Future of Time, Quantum Clocks in the Invisible Universe with Mariana Safranova. That will be here. It's not next week, excuse me, it's 2 weeks, thank you. All of the dates are on the back of your program. Please do RSVP because we do fill up and we want you to come and join us. This lecture will be filmed for educational purposes. If you have any questions, please come find me. Again, my name is Marisa. And without further ado, I'm going to turn it over to Dan.
Thank you. It's great to see everybody out here. It's great to see the snow, too. I'm Dan Freed. I'm a professor of mathematics at Harvard, and I've been coming to the center very regularly since the late 1980s, in fact. You might ask, what's a mathematician doing at a physics center? But it's actually been a very important place for me and many of my colleagues. It's a unique place where we can engage with physicists and learn each other's language, learn each other's ideas, and really has led to lots of deep interactions over the years between our fields. And it's something that I think is very characteristic of this center, that it's about physics, and there's a lot of core physics, but also physics reaching out to other disciplines. And that's something that's really special here. It's a place with the beauty of nature. You can think larger thoughts, think open thoughts, and be open to collaborating across fields. So I think that also ties in with the Aspen idea, with Pepke and what happened in the late 40s, and what really started modern Aspen. So that brings me to our housing project, which is called Housing the Aspen Idea. I'm sure many of you are aware. We're actually in front of City Council right now, and there are a few posters out there. You can go to our website, aspenphys.org, and learn more about this project, which is meant to sustain the center into the future and bring you events like this. So that brings me to our speaker, Jake McNamara. I first met Jake when he was an undergrad at Harvard, and he did get his bachelor's degree in mathematics, but then went a little sideways into physics, where he got his master's degree and also his PhD. Jake then became a postdoc at Caltech in 2022, and last year moved to Stony Brook, where he currently is a postdoc as well. And he just told me he's being pulled more and more back into mathematics, so that really warms my heart. And without further ado, Jake.
Thank you. All right. So first of all, thank you, Dan, for the nice introduction. Thank you, everybody, for being here. This is my third time at the Aspen Center for Physics. And as Dan said, this is one of the most beautiful and inspirational places where we come to think about physics, collaborate on physics, and as it is my great honor to do today, share some physics with you. So my talk today is about symmetry in theoretical physics, particularly symmetry in the context of gravity. Gravity is my field of specialty, specifically quantum gravity, meaning treating gravity compatibly with the rules of quantum mechanics. But of course, the story of symmetry is much older. It doesn't start with Einstein. Symmetry is an ancient concept. It goes back to our most ancient civilizations, and probably deep into prehistory. Symmetry shows up in all walks of human life. It shows up in art, for instance, in the mosaics which inspired this image you see here. It shows up in architecture, in biology. We see it in animals. We see it in molecules. And it shows up in physics, and it shows up in math. So symmetry, our obsession, our human obsession with symmetry, has not ended. Symmetry is one of the most active fields in theoretical physics right now, and has been for the past, say, 10, 15 years. And you might wonder, why now? Why is symmetry so exciting right now? You might think that being an ancient idea, we might know all there is to know about symmetry. We might know all the ways something could be symmetric. And it turns out that that's not the case. About just over 10 years ago now, in 2014, there was sort of a watershed paper, this paper on generalized global symmetries. This paper brought together ideas that had been brewing in the fields of high-energy theoretical physics, in mathematics, in condensed matter physics, and string theory, and brought all those ideas together into this new concept of a generalized global symmetry. So we've learned many new ways that a physical system can be symmetrical, and as a result, there's lots to do. You can see the citations for this paper have just skyrocketed. It's the fourth most cited paper in high-energy theory in the past 15 years. Don't be fooled by the dot for 2026. We're just getting started with 2026, and I expect it to be up at the top, if not higher, by the end of the year. Of course, to go along with all of this research, there's been a lot of academic activity on symmetry. I'm here this week as part of a workshop, I guess a conference, on generalized symmetries and defects in quantum field theory and gravity. This is just the latest in a long list of programs at the Aspen Center for Physics that have focused in one way or another specifically on the concept of symmetry and symmetry in physics. It's also the focus of a number of large research programs. One of these is the Simons collaboration on global categorical symmetries, and the other one, very close to my sort of academic home, is the Swampland Program, which specifically is interested in symmetry in the context of gravity. So what I want to explain to you today, I want to explain how physicists think about symmetry, why we're excited about symmetry, and particularly how symmetry has played an absolutely central, crucial role in the development of our understanding of gravity over the years. And so I'm going to take you on a tour from Einstein to today. We'll see how symmetry has played a role time and time again in the development of our understanding of gravity. And then at the end, I'll look forward and describe a little bit about some of these new generalized symmetries and what they tell us about gravity and the world around us. So I'd like to start with some real basics. So what is symmetry? So a symmetry, in general, is a transformation of some thing, some object, some physical system, some physical theory, some idea, which preserves all of its relevant properties. So to give a simple example, let's think back to high school geometry. We have two triangles here, and probably everyone can tell that they're the same shape. But if you didn't know they were the same shape, or you had someone you were trying to convince they were the same shape, you could convince them they're the same by making the following argument. You could say that you can notice that by taking the triangle on the left and reflecting it across the line, you get the triangle on the right. Maybe not so remarkable in this case, but this is a way to see, given a symmetry, you can tell that two things share all of their properties if one is transformed into the other by a symmetry. I should emphasize that what's symmetrical here is not the triangle. I made sure that this is not a symmetrical triangle. What's symmetrical is the laws of Euclidean geometry. You could, of course, ask for a particular figure to be symmetrical, like this diamond, but I'm mostly going to focus on the first kind of symmetry in this talk, a symmetry which takes you between things that, at first glance, do not seem to be the same. And this is when symmetry can be most powerful, most sort of revolutionary. It can teach us that things we didn't think were the same are actually the same. Of course, again, in this case, maybe that's not so interesting or surprising, but we'll see more and more surprising examples as we go along. Now, I'd like to linger on this example a little bit and sort of unpack what do I mean by the same. So these two triangles are not literally the same. They're the same shape. How can I distinguish them? How do I know they're not literally the same? Well, I can look at the screen, and I can point to the right, and I can see the triangle on the right. And I can point to the left, and I can see the triangle on the left. So what that means is that I can distinguish them even if the laws of Euclidean geometry can't. To put it differently, the symmetry which reflects the triangle is a symmetry of the plane, but not a symmetry of the combined system of me and the plane. This highlights the fact that symmetry is in general relative. Symmetry is a property of a system, but also a property of a system interacting with another system. But there's something much more dramatic I could imagine doing, which is to reflect not just the screen, but myself, and for good measure, reflect all of you, reflect all of Aspen, all of the world, all of the universe. And if I were to do that, I assert that you would end up in a universe which is literally the same as the universe we currently live in. In this sort of reflected universe, absolutely everything we could ever measure, we could ever observe, experience, would be exactly the same as before we reflected. And there's a deep principle at play here. It's probably a principle you've heard before. If it walks like a duck and talks like a duck, then it's a duck. Being a physicist, or maybe a mathematician, I should be more precise. I should say that if it walks like a duck and talks like a duck and does absolutely everything else exactly like a duck, it's not probably a duck, it is a duck. And phrased this way, I think I intend this to be painfully obvious, but I also claim that this is a profound truth about the universe. This happens a lot in physics, where the most profound ideas are painfully obvious when you think about them the right way. Now, being a deeply profound idea, this principle that things are determined by their properties, by the ways in which you can interact with them, goes by many different names in many different contexts. It's played an important role in a lot of different fields. So in philosophy, this may be the first recorded clear statement of this idea, is Leibniz's identity of indiscernibles. It's just the same thing I said before. Two things are the same if they have the same properties. If they are indiscernible, meaning you can't tell them apart, then they are identical, the same. The contrapositive of this is also very useful, which is if things are different, then you should be able to tell them apart. You could say it's the discernibility of non-identicals. A more recent instance of this same principle appeared in 2009, and it goes by the name of the univalence axiom. This is an idea due to Voevodsky. This is a linchpin idea in a mathematical field known as homotopy type theory, which is connected to category theory and other fields of mathematics that directly interact with physics in this generalized symmetry program. And what's the idea here? Sameness is equivalent to equivalence. What does that mean? It means that a good physical theory or a good mathematical theory should not allow you to talk about sameness of things or identity between things, except insofar as you have a symmetry taking you from one to the other. I think this is just, in some sense, common sense. If you have something you're thinking about, some object in the universe, some state of the universe, it's not meaningful to talk about being the same except insofar as you can identify the two. You have a way of going between them. So this is an idea that's been very important in mathematics recently. But there's one more instance of this same principle that's very close to my heart as someone who thinks about quantum gravity. And it goes by the following slogan: quantum gravity has no global symmetries. So a global symmetry, this is physics jargon for a symmetry between things which are not literally the same. So we saw an example. The symmetry which reflects the triangle on the screen is a symmetry between things that are not literally the same. And this is a very useful idea in physics. It's very reasonable to think about global symmetries when you have a system in front of you that you're studying. Of course, this is almost always what we're doing in physics. We have some system that's not the whole universe that we can think about transformations. Say you have some material on a lab table in front of you, and you can think about the transformations of that material that leave its properties invariant, but don't also transform the whole universe. However, when we want to think about gravity, when we want to think about quantum gravity, it's not so reasonable. Gravity is fundamentally a universal thing. As we'll see, gravity is connected to the geometry of space and time. It's a property of the universe as a whole. You can't split it apart. And so if you want to think about symmetries in the context of gravity, you have to take seriously the fact that if we're talking about symmetries which transform the whole universe, they had better take you to a configuration, a universe, which is literally the same. In other words, quantum gravity should satisfy this duck principle. If it walks like a duck and talks like a duck, then it's a duck. So I should put up some warnings, some warning signs. This statement is, strictly speaking, a conjecture. Quantum gravity is in a bit of a difficult situation. We neither have a complete theory of quantum gravity, nor do we have any experimental evidence for quantum gravity. The reason for this is just a matter of circumstance. Quantum gravity is only important when things are very strongly gravitating and quantum mechanical. And it just so happens that almost everything in the universe is not both of those things at once. So anything I say about quantum gravity is going to be in some sense conjectural. So with that warning out of the way, I should say I really do believe this. And I believe this because I think it's common sense. I can't really conceive of a universe where this wasn't true, where there would be distinct universes where we can't tell anything apart, but for some reason they count as different. So this is a conjecture, but it's, I think, a well-motivated conjecture. And as we'll see by the end, it's a useful conjecture in constraining physical theories. So with that philosophy out of the way, I'd like to now take us on a history of gravity, highlighting the role of symmetry. In particular, highlighting the themes of symmetry, identity, and relativity. So again, I apologize, the story does not start with Einstein. The story starts circa 1590, when Galileo showed, by dropping objects off the Leaning Tower of Pisa, that all objects fall at the same rate absent air resistance. This is the first hint of the universality of gravity, the fact that gravity affects everything the same. This is not true of every force. Electromagnetism only pulls on charged objects, but not on neutral objects. The next important moment is in 1666, when Newton writes down the universal law of gravitation, supposedly after seeing an apple fall from a tree, and noticing, in some sense, a symmetry, that the force pulling the apple is the same as the force pulling the moon and holding the moon in orbit. And Newton's law of gravitation held for quite a while. It's a pretty good approximation for almost every purpose. But in 1915, Einstein upended this sort of Newtonian paradigm with his general theory of relativity. This was a dramatic reinterpretation, reimagining of what gravity even is. He connects gravity to the geometry of space and time, and really sets the stage for all modern thinking about gravity in theoretical physics. Not only is this a conceptually, aesthetically pleasing theory, it's also a practically important theory. You need the corrections to Newton's theory from Einstein to understand the orbit of Mercury near the sun. You need it to synchronize our GPS clocks. And so really, Newton is a good approximation, but Einstein's theory is more correct. This is not the end of the story. Einstein's theory, though very profound, very useful, very interesting, is ultimately a classical theory. It doesn't have the fundamental uncertainty inherent to quantum mechanics. And so over the past, say, 100 years, we've been trying to understand how to combine Einstein's theory with quantum mechanics. The most important conceptual discovery in this direction came in 1974, when Hawking showed that black holes, rather than these inert objects, actually give off radiation due to quantum mechanical effects. And this result of Hawking is something that I think we're still grappling with in our research. We're trying to understand how this works. Part of the issue is that, as I said, we don't have a complete theory of quantum gravity. One of the best conceptual explanations for Hawking's result came in the 90s from 't Hooft and Susskind, who proposed what's known as the holographic principle. So the holographic principle is yet another dramatic reinterpretation of what gravity even is, and is where our story will stop for now. So I'm going to focus on two of these. I'm going to focus on Einstein's theory and the holographic principle, and explain the sense in which both of them arise as the recognition of a new symmetry of nature, a new way of things being the same that we didn't know previously. So what was Einstein's insight? Einstein's main insight in 1915, leading to his general theory of relativity, is what's known as the equivalence principle. This is the recognition that gravity and acceleration are the same thing. Again, this only works because all objects fall at the same rate. If objects fell at different rates, then we couldn't identify gravity and acceleration, because acceleration, if you are accelerating, everything else accelerates at the same rate. To get some sort of visceral understanding of this equivalence principle, if you haven't thought about it before, think about the feeling you get when you're in a car and the car takes a sharp turn and you're flung against the outside. You could also think about the feeling when you're on a roller coaster or on the slopes. You go over a bump or a hill and you momentarily feel like you're floating. And you can try to imagine that currently, rather than in a room on Earth, this room is out in space being pulled by a rope upwards, accelerated upwards, yanked upwards. And if you think about it, you can maybe forget the fact that we're so familiar with gravity, we're so used to being in a gravitational context, that you can recognize that the thing pushing us down to the floor is exactly the same as the thing that pushes you to the side of a car when it turns. We're currently being flung against the ground in just the same way. So one story about this, so when I was a young science-obsessed kid, I had been reading pop-sci books, and I wanted to show my friends how cool it is that when you're in an elevator, and the elevator starts moving downwards, and you jump, you feel yourself floating a little bit. Now don't try this, because the end of the story is that, of course, a bunch of kids jumping up and down in the elevator made it break. And the fire department had to come, and it was ultimately embarrassing. But I still think it's a cool idea. So what Einstein's equivalence principle is telling us is that there's a new symmetry of nature. This identification between acceleration and gravity is a symmetry. In particular, it's a symmetry that turns our motion through space into, in some sense, space's motion through us. So acceleration, of course, has to do with our motion through space, or the rate of change of our motion through space. But we like to think of ourselves as sitting still, like right now while we're sitting in a lecture. If we're going to sit still, and gravity is the same as acceleration, then space itself had better be moving. So what I've drawn is on the left some object moving through space in the usual way we imagine. But on the right, I've drawn what is supposed to be an equivalent description of the same thing, which is the object at rest and space moving. The technical name for this is what's known as diffeomorphism symmetry, as the symmetry that goes from one side of this picture to another. And diffeomorphism symmetry is something that we understand very well. Mathematically, it's well established. We know how to write down physical theories that have this symmetry. In fact, in many ways, Einstein's theory follows immediately from this symmetry. So the picture we end up with is that gravity is space-time falling. So we have the Earth, and we have the space around the Earth, and that space is constantly falling into the Earth. That's what's happening right here. We're sitting here, space is falling down, so we get pushed to the ground. I think a useful analogy is if you're sitting at a dinner table, and you have some dish across the table that you want, and you don't want to get up and walk around. So instead what you do is you grab the tablecloth and you start pulling it. And you pull the tablecloth and the dish comes towards you. And that's what gravity is doing, is it's grabbing space and pulling it in. If you like, this is the gravitational field. The space-time itself is the gravitational field, which transmits the pull of the Earth out to some object and pulls it inwards. So this can be expressed in terms of Einstein's equation. This is Einstein's the equation expressing his general theory of relativity. And again, it's really a direct consequence of this symmetry. It's the most obvious thing you write down once you recognize that our world is invariant under the symmetry that turns acceleration into gravity and vice versa. So on the left, we have a term which explains how space-time moves. You may have heard that Einstein's theory is about how space-time bends, but space bending as a function of time is just space moving. And so I think, personally, I find it a little more intuitive to think of it as the motion of space. On the other side, we have a term that describes where stuff is. And so in the case of the Earth is a source. It sits there, it's a massive object, and it pulls on space. So as I said, Einstein's theory has been incredibly well tested. One of the most dramatic consequences, implications of Einstein's theory is what's known as a black hole. This is a scenario where that falling of space-time runs amok. It runs out of control. Space is falling inwards. You can imagine like a waterfall. It's just constantly falling in. Whatever object may have created the black hole is deep within this gravitational well, and the space is just constantly falling in faster and faster. The black hole is characterized by what's known as a horizon. This is the surface where space-time is falling inwards at the speed of light. And because it's falling in at the speed of light, then nothing can get out. So if you try to get out, you move against space, but the current is too strong. And it pulls you in. It's moving faster than you can possibly move. And so nothing can escape classically from a black hole. Now, black holes are fairly perplexing and fairly disturbing. In fact, for a while, people hoped that they weren't real. Einstein himself wrote a paper trying to argue that black holes can't possibly form in astrophysical scenarios. But we don't have that option anymore. And we don't have that option anymore because we've seen them. We have pictures. These are honest-to-God pictures of black holes. The first one is a black hole called M87 star. It's a supermassive black hole at the center of some other galaxy. The bottom picture is the black hole Sagittarius A star, which is the black hole at the center of our universe. Of our galaxy. It's our black hole. And there they are. We've taken pictures of them, just like you would with a camera. The camera here is a very powerful camera called the Event Horizon Telescope. No affiliation of mine, but a big fan of their work. The Event Horizon Telescope is an array of radio telescopes placed all around the Earth. Here are a couple of them that together take a picture of the black hole. The idea at play here is the same as with a wide lens camera. If you want to get better resolution, you need to make your lens bigger. And so by making the lens the size of the Earth, you can get enough resolution to have even these kind of blurry, but I think still incredibly exciting images. So black holes are real. They're objects out in the universe, and we have to deal with them. We can't sweep them under the rug. We have to understand how they work. So black holes have played an increasing role in the way we think about quantum gravity, centered mainly around what's known as their thermodynamics. This means their temperature, their response to external pressures and forces, how they behave as a sort of thermodynamical system. And classically, they're pretty inert. In the previous picture, you see a cloud of gas, hot gas around the black hole. I'd like to tell you that this is the horizon. It's not. It's the shadow of the black hole. So a little disappointing. But the black hole is surrounded by hot gas, but the black hole itself is relatively inert. Things fall into the black hole, and they don't come out. And so it's perfectly absorbing. It doesn't behave like it has its own dynamics. But this is not true quantum mechanically. Quantum mechanically, what was shown by Bekenstein and Hawking in the 70s is that black holes actually radiate. They have a rich thermodynamics. You can understand this in the following way. Quantum mechanics means that there is a fundamental indeterminacy in where objects are. And that means that something, if it's a little bit uncertain whether it's in or outside of the horizon, it has some probability to tunnel out and come out. You can also think of it as some uncertainty in the energy. What can happen is that something with a little bit of negative energy falls into the black hole, which ends up extracting energy from the black hole at the end of the day. There's various different ways to say it. Maybe the most convincing is that you do the math and you check and that's what happens. But it really is fundamentally a consequence of quantum mechanics, just applied directly to the black hole spacetime. And in fact, the black hole thermodynamics takes a remarkable form, a remarkably simple form. When viewed from the outside, black holes behave exactly like a thermal quantum system living on the horizon, meaning that they have the same number of degrees of freedom as something that sits at the horizon. They have the same temperature, they have the same thermodynamic quantities. And if you've been following along, then maybe you know what's coming next. Maybe black holes do not just look exactly like a thermal system living on the horizon. Maybe they are a thermal system living on the horizon. So this is what's known as the holographic principle. This is an identification, a theoretical proposed identification of the black hole on the one hand with some, in principle, a priori unrelated system living on the horizon of the black hole. To explain this a little bit more, the black hole has some big interior. There's some space inside the horizon. And what holography does is it replaces the space inside the horizon and all of the physics happening inside, all of the dynamics, whatever fell in, and it replaces them with some degrees of freedom, some physical system that just sits at the horizon. And in the description, the holographic description, the interior is gone. The interior has been replaced. The interior is supposed to be equivalent to the degrees of freedom on the horizon. This is an example of what physicists call a duality. Duality is a symmetry between physical theories. It's two physical theories that ultimately are literally the same. And this, again, can also happen sort of due to quantum mechanics. These descriptions look naively very different. And if there was no uncertainty, they would just, on the face of it, look, they're different. But quantum mechanics introduces enough blurriness, enough uncertainty, if you squint your eyes, that different classical descriptions of the same physics can end up, different classical descriptions of different physics can end up producing the same, exact same, literally the same quantum mechanical system. I don't think this one is intuitive. You can't just squint your eyes, but it's this is the implication, I think, of what we've learned about black hole thermodynamics. And the holographic principle really wants to be a new symmetry of nature. We want to say, just like we did with Einstein's theory, that, okay, we have a new symmetry, let's go and write down a theory which is defined and has this symmetry. In contrast to Einstein's equivalence principle, we don't have a good mathematical understanding of this. We don't know what it takes to write down a physical theory that's invariant under holography. We think that string theory is, due to some very nice arguments of Juan Maldacena, but string theory is incomplete, and so we can't just check, and we don't have the mathematical or conceptual tools to describe holography. In fact, this is something that I think a lot about, and I'm very excited about. I'm excited that some of these new notions of symmetry that we've been seeing might play some role in understanding what it means to have this symmetry. Now, holography is also conjectural, but for now, let's take it as a given. And let's see what holography implies for these questions of identity and sameness. So what holography tells you is that in gravity, every aspect of the interior of the black hole is encoded in some way on the holographic screen. What that means is that the only properties of physics in the interior that can even be meaningful are the properties that you could describe at the horizon. In other words, in quantum gravity, if two things are distinct, they had better be distinguishable from far away. from doing physics far away from the system you're trying to study. It turns out that this fact that distinct physical scenarios should be distinguishable from far away is also another incarnation of the principle I said before, no global symmetries. In physics, whenever you have a symmetry that takes you not between distinct things, but between things that are literally the same, the information of that symmetry can always be transmitted out to the boundary of the space you're considering. And so the last thing I'd like to do in this talk is I'd like to ask, is this true in our universe? Does our universe have this property? Can physical properties of our universe be distinguished from far away? And surprisingly, I'm going to tell you that the answer is no. I'm going to give you an example of how the answer is no, at least with our current understanding of physics in the universe. And this puts us in a bit of a, well, either a bind or an exciting an opportunity, because it means that either we have to give up holography and give up the fact that a black hole looks like a quantum system on the horizon but isn't, or we have to change something to make this other example of a distinction without a difference go away. So to explain this example, I'm going to need to review a classic experiment in quantum mechanics. This, in principle, has nothing on its own face to do with gravity. But this is an experiment that is intimately tied to one of these new notions of symmetry. And so I'm going to try to explain one of these new notions of symmetry, how it appears in our universe, and what concrete predictions it leads to if we take this principle. So this is what's known as the Aharonov-Bohm effect. The experimental setup is you have some magnetic field, and you send in a beam of electrons that's coming in from the left, and you split the beam. You have some of the beam go around to the left, some of the beam go around to the right, recombine, and let it hit a screen. The electron is a quantum mechanical particle, so it can behave as a wave, and in this case it does behave as a wave, and it creates what's known as an interference pattern on the screen. This interference pattern is the alternating peaks and troughs of the electron wave. This in and of its own right is maybe not, well, it's exciting in its own right, but it's not part of the story I'm trying to tell. The exciting part is what happens when the magnetic field is increased or decreased. So that was a little quick. As you increase the magnetic field, what you see is that the interference pattern moves over to the side. The implication is that from doing experiments far away from the magnetic field, we can tell that it's there. So that's what I was trying to get to. The magnetic field is something which in our universe we can tell whether or not it's there by just doing experiments far away from the thing in question. But we can now ask, what about the electric field? So in this experiment, we put a magnetic field and we measure it using an electron. What if we have an electric field? Well, we might switch the roles of electricity and magnetism. And so what we should have is a magnetic monopole. So magnetic monopole is a particle whose existence has been theorized in various different contexts. It's never been observed. When you have a bar magnet with a north and a south pole, and you split it, it ends up being just two smaller bar magnets, each with their own north and south poles. A magnetic monopole would be a particle which is just magnetic north, without magnetic south to complement it. What we have, the way magnets work is magnets are made out of what's known as magnetic dipoles. They have a north and south splitting, but they don't have overall north or overall south. And to do this experiment, we would need a magnetic monopole. So if you believe that the universe should satisfy the property that physics can be distinguished from far away, then we need a magnetic monopole. Then there must be a magnetic monopole in our universe. And I think it's quite remarkable that these almost philosophical considerations about sameness, about symmetry, lead us directly to the prediction that our universe had better have a magnetic monopole. In other words, our universe would be, in some sense, incomplete without a magnetic monopole. Now, I don't want you to get too excited. Um, Modifications of the argument I've been presenting, which use what's known as the weak gravity conjecture, give a theoretical upper bound for the mass of the monopole, which is 4 times 10 to the 15 tera electron volts. To give you some context, the highest energy we've reached in a collider is on the order of 1 tera electron volt. So this is 15 orders of magnitude higher. So we're not going to see them anytime soon. But nevertheless, I'm interested in what the universe is made out of. I think it's interesting to believe that there's a magnetic monopole. And there's other contexts where you might hope to see imprints of a monopole. For instance, in cosmology, you might hope to see imprints of monopoles in the early universe, and they might have imprints on things like gravitational wave signatures, things like that. So what I've been explaining, this example, is an example of one of these new kind of symmetries. So to explain that, let me emphasize that this effect is a property of a path in space-time. The Aharonov-Bohm experiment sends in an electron beam, splits it around 2 ways, and lets it hit the screen. And to see the effect, you have to go around both ways. You have to travel along a path in space-time. Many of the properties of physics we like to think about are properties of a point in space-time, properties you can measure just doing physics in one location. But we've learned that physics has properties that are not just localized at one location, but really are intrinsically properties of a path. And we have a notion called one-form symmetry. This is a symmetry, it's a transformation of the system, which does nothing to any of the local properties, but only transforms the properties of the path. The fact that this is even possible is relatively new. The 1 here refers to the 1 dimension of the path. You could have a 2-form symmetry, which transforms the properties of surfaces, etc. And what I've been explaining is that without a monopole, our universe would have a global 1-form symmetry. It would have a transformation which takes it to a distinct state that we couldn't tell the difference because we couldn't have a monopole, we don't have a monopole, and we couldn't do this experiment. So if we believe that our universe should be, the physics in our universe should be determined by its properties, meaning that if we have 2 different universes where we can't tell apart in any way, then they should be the same. This directly leads us to the idea that there should be a magnetic monopole. So this brings me back to the workshop we have here and the research program that's ongoing. This is one of the new notions of symmetry. There's a bunch of them. They have different names: higher form symmetry, higher group symmetry, non-invertible symmetry. This one is a little bit mind-melting. It's a symmetry where you throw out some of the degrees of freedom of your system, and then quantum mechanics puts them back in, and you end up back where you started. And we just keep learning more and more. We keep seeing more and more examples of these symmetries. At first, we thought that these symmetries were relatively exotic. Maybe you have to come up with some very contrived system in some different number of dimensions than we live in to see them. But that's not the case. They show up all over the place in physics. They show up in just about every system you can imagine, including things like the standard model of particle physics. And so what we're doing in this workshop, in this conference, and more broadly in this research program, is we're trying to understand, what do they tell us? What are the transformations of the universe that they enact, and what lessons can we learn from them for quantum gravity, for physics in our universe? In particular, can they help us build a quantum theory of gravity? That's, I think, for me at least, one of the main goals. So with that, let me thank you for your attention, and I look forward to your questions.
Thanks, Jake. Thanks, Jake, for a beautiful lecture. So we have lots of time for questions. So if you have a question, please raise your hand, and the microphone will be brought.
Hello. You mentioned that black holes have shadows. Could you explain?
Yeah. Here, let me go back. So what is a shadow? A shadow is that you have some light and you have something blocking the light, and the shadow is the result of some part of it being lit and some part having the light blocked. Black holes in particular are black. They absorb light, and so you don't expect to see light coming directly out of the black hole. And so that's why you would call it a shadow. It's a little bit bigger than the radius of the black hole, the horizon, because if you have anything behind it, there's sort of an effect where it expands. The shadow is bigger than the object itself. Yeah.
Okay, for a non-physics math person, could you, is this on? Could you please re-explain the theories behind whether if there is a monopole or not a monopole, and how that, I don't know if I'm just misunderstanding, but does that relate at all to potential existence of a mirrored universe? And if so, what is the relation?
Yeah. So the connection. So the monopole, as I said, is a theorized particle. We've never seen one. People have talked about them. There's various extensions of the standard model of particle physics, meaning various predictions for new physics that would predict a monopole. Never seen one. And our current theory of the universe does not allow for a monopole. The connection is through this generalized sort of symmetry. The point is that we can do a transformation of the property of the path. This is this generalized notion of symmetry, where we take the path and we do something that may sound a little bit twisted, which is we shift what the Aronoff-Bohm effect would be if we did have a magnetic monopole. And we know that that's something we can do. It follows just from the rules of electromagnetism. And if we don't have a magnetic monopole, then that's a symmetry, meaning it's a transformation that preserves everything we can possibly measure. And if we think that those transformations should not be allowed in the real world, then we would need a monopole. Because with a monopole, we can measure that property and we can distinguish between before and after. Yeah, so that's the connection.
I'm not a physicist, I'm just curious. With everything that we know about gravity as acceleration, what is the future of anti-gravity, where we think that we have seen it before, usually in extraterrestrial technology? People see large items floating without wind, without fire coming down. Is any of this leading towards understanding how to counteract it?
I would say no, unfortunately. I mean, it would be great if we could have anti-gravity. That would be very useful. Maybe the reason why I would say no is because of this fact that I explained of the universality of gravity. Gravity pulls on everything the same. Electromagnetism, we have anti-electromagnetism. A positive and a negative charge attract each other, but a positive and positive charge repel each other. But gravity pulls everything together. And because it's connected to the geometry of space and time, you can't get away that. Because it's the geometry of space and time, that's why it pulls on everything the same. Because if space is moving, everything feels that, because everything lives in space. So to have something like anti-gravity or like negative gravity, you would really need to go beyond. You would have to break down Einstein's theory, which, maybe, but yeah.
More questions?
What about the breaking of
One
symmetry?
second, the mic's starting.
What about the breaking of symmetries? We know that there's a symmetry between matter and antimatter, but it seems like matter is more prevalent than antimatter.
Yes.
Any way to predict which symmetries should be broken and why?
Yes. This is a fairly broad question. I mean, it's a good question, but a very broad question. For matter and antimatter, we know that there are processes which can lead to an offset in matter versus antimatter. The standard model of particle physics allows for production of more, say, baryons than antibaryons, baryon being a particle like a proton or a neutron. Generally, the question of whether a symmetry gets broken, meaning whether the symmetry, the system, let me give a very straightforward example. So the plane geometry, just for everyone's context, plane geometry has the symmetry of reflection. The triangle breaks the symmetry because it itself is not symmetric. So that's what we're talking about here. The question of whether symmetries get broken is one of the most important questions when you're thinking about a system. This is part of the whole paradigm of using symmetries as a way to constrain phases of matter, for instance, whether the symmetries can be broken or don't get broken. Maybe one more comment is just that what I'm saying with the monopole is that the symmetry we would have without the monopole gets broken in the presence of the monopole. So this is a feature of these generalized symmetries, where the generalized symmetries get broken by the existence of a particle rather than the lack of invariance. The lack of invariance corresponds to the existence of a particle.
More questions? In the back.
Do you have an example of like where a particle symmetry is connected to like a surface or flux symmetry, like a two group or something like that?
Oh. So you clearly have some experience with this stuff. So I was talking about normal symmetries, which are symmetries that do something to the properties measurable at a point in space. And then there's the one-form symmetries, which do something to the properties measurable along a path. There's also the possibility that these two symmetries might combine together and interact with each other in non-trivial ways. For examples of those, maybe we can talk about it later because that would probably get too technical. But I'm happy to discuss. Yeah.
Other questions? Okay. If not, I want to first thank the Nick and Maggie DeWolf Foundation for their support of these lectures. I want to thank all of you for coming out and for your great curiosity and support. And I hope we see you again on February 25th, the next lecture in the series, The Future of Time, Quantum Chaos in the Invisible Universe. And finally, let's thank Jake again for beautiful